It's time to look at what makes a spacecraft work. In this video, I'll talk about the essential subsystems that give a spacecraft its power, stability, brains, and mobility. These are the core engineering building blocks that turn a design into a functional mission. Every spacecraft needs electricity to function, and that's the job of the electrical power system, or EPS. This system generates, stores, and distributes power to every component on board. The primary way spacecraft generates power is through solar arrays, commonly known as solar panels. These large panels are covered with photovoltaic cells, which convert sunlight directly into electricity. For missions far from the sun, where sunlight is too weak, engineers turn to radioisotope thermoelectric generators, or RTGs. RTGs convert heat from the natural decay of radioactive materials like plutonium into electricity. The generated power needs to be stored for when the spacecraft is in shadow or needs extra power bursts, which is where batteries come in. Power distribution involves a complex network of wiring, power management units, and voltage regulators, ensuring each subsystem receives the correct power. For a spacecraft to do its job, whether it's pointing a camera at Earth, aiming an antenna for communication, or simply keeping its solar panels facing the sun, it needs to know its orientation and be able to control it. This is the role of the Attitude Determination and Control System, or ADC. Attitude determination is about figuring out the spacecraft's current orientation in space. This relies on a set of sensors, including star trackers that image constellations, sun sensors that detect the position of the spacecraft with respect to the sun, magnetometers that measure Earth's magnetic field, and inertial measurement units that use gyroscopes and accelerometers to track changes in orientation. Once the attitude is known, attitude control corrects or changes it using actuators. These include reaction wheels, which are electrically powered flywheels that rotate the spacecraft by changing their speed. Momentum wheels, which store angular momentum for a stable platform. Thrusters, both chemical and electric, that provide small bursts of force. And magnetic torque rods that interact with Earth's magnetic field. The ABCS is important because without precise attitude control, a mission cannot collect scientific data, communicate effectively, or even maintain its power balance. We discussed thermal extremes in our first video of this series, but here we see how engineers tackle them. The Thermal Control System, or TCS, keeps all spacecraft components within their specific operational temperature limits, preventing overheating and freezing. Thermal control relies on smart material choices and designs such as MLI, multi-layer insulation blankets, and specialized coatings. Active thermal control adds powered elements for more precise regulation, including heaters that activate when components get too cold, heat pipes that efficiently transfer heat, and louvers that control heat release. For very sensitive instruments, cryocoolers actively remove heat to maintain extremely low temperatures. The TCS is a constant battle to balance internally generated heat with heat absorbed from the sun and heat radiated into outer space. The spacecraft's intelligence and ability to move come from the command and data handling and propulsion subsystems. The command and data handling subsystem includes the onboard computer, or OBC, which runs flight software, processes data, and manages all operations. These computers are often redundant and radiation hardened. A complex network of data buses connects all subsystems, allowing them to communicate. The command and data handling subsystem also manages telemetry, which contains the health data sent to Earth and processes commands sent from ground control. An important component is also the fault detection, isolation, and recovery FTIR system, which is the spacecraft's ability to detect, diagnose, and fix problems autonomously. The propulsion subsystem is the spacecraft's muscle, allowing it to move and change its orbit. Its main purpose include inserting the spacecraft into its final orbit, performing station keeping to maintain its correct position, providing precise attitude control, and safely deorbiting the spacecraft. There are several types of propulsion. Chemical propulsion uses a chemical reaction to expel hot gas, creating thrust. This includes solid rockets for large short bursts and liquid rockets, either monopropellant or bipropellant, which provide high thrust. Electric propulsion, like ion thrusters or Hall effect thrusters, uses electricity to ionize and accelerate a propellant. These thrusters provide relatively low thrust but are incredibly fuel efficient, achieving high specific impulse, or ISP. Cold gas thrusters are an example of simple propulsion systems that expel inert gas for small, precise adjustments. The choice of the propulsion system on board depends heavily on the mission's delta-V requirements and available power. These core subsystems, EPS, ADCS, TCS, Command and data handling, or CNDH, and propulsion are the fundamental building blocks of every spacecraft. Along with these is the spacecraft structure that carries the loads. There is communication subsystem with the antenna connecting with the ground stations on Earth. Each subsystem is a marvel of engineering in itself, designed to operate reliably in the most unforgiving environment imaginable. Their seamless integration is what makes space missions possible, turning a collection of parts and components into a sophisticated machine which is capable of scientific discovery and exploration. In our next video, we'll see how these complex parts come together through the process of assembly, integration, and test, or AIT. And we'll then talk about some exciting new developments in space technology. Do not forget to check the link in the description for more space-related educational resources, and stay subscribed to this channel for the next video. Thank you.